Hello students, welcome back to my channel. This video I am going to explain LANGMUIR adsorption isotherm. Previous video I have explained Freundlich adsorption isotherm. This is the second type of adsorption isotherm students. Okay. So before going into LANGMUIR adsorption isotherm, whoever is watching for the first time, kindly subscribe the channel, and who have already subscribed, don't forget to like the video and share the video with your friends students. Okay. Now see, before getting the LANGMUIR adsorption isotherm equation, we need to understand few points under this topic students. The major points to be noted or to be followed under this LANGMUIR adsorption are: first point is the adsorbed layer on the adsorbent is monomolecular or unimolecular in thickness. Okay, that means it will be in a single layer students. The adsorbed layer, you can find it in a single layer. Okay, it's unimolecular or monomolecular in thickness. First point. Second point is adsorption takes place on the adsorbent at fixed sites and there is no attraction or interaction between the molecules which are adsorbed. Okay, try to understand students. Adsorption takes place on the adsorbent at fixed sites, at particular sites, and there will be no interactive forces between the molecules that are adsorbed. Third point, surface of the adsorbent is uniform. Okay, it's unimolecular in thickness, adsorption taking place at fixed sites, no interactions between the adsorbed molecules, surface of the adsorbent is uniform. Now, the process of adsorption, we find it has two opposing processes. Two opposite processes. One is adsorption and the other one is desorption students. Adsorption is also called as condensation and desorption is also called as evaporation. Okay, 4 points you should mention under LANGMUIR adsorption. Okay, at the beginning, that means initially or in the initial stages, rate of condensation will be high or is maximum at initial stage. Why? Because surface of the adsorbent remains free. Okay. So rate of condensation, what is meant by condensation? Nothing but adsorption students. Initially, okay, before the adsorption has taken place, the whole surface will be free and hence rate of condensation or adsorption will be very high. We can say it will be maximum. Now slowly adsorption started. That means molecules started getting adsorbed on the surface. As the surface becomes gradually covered, what happens? Rate of condensation becomes smaller and smaller. Initially, the whole surface is free students. Hence, rate of condensation we say that it's high or maximum. Slowly, as the surface becomes gradually covered, rate of condensation decreases. Okay. Now, on the opposite side, what is the second opposite process students? Evaporation or desorption. On the contrary, the initial rate of evaporation is almost zero. Why? Because there are no molecules that are adsorbed on the surface. Hence, we say that the rate of evaporation is almost zero. Whereas rate of condensation maximum, rate of evaporation is zero. But increases with time. Why? Because the surface gets adsorbed. Surface of the adsorbent becomes more and more covered with the adsorbate molecules. Okay students, you understood these 2 points ma? Initially rate of condensation will be maximum ma? Why? Because surface of the adsorbent is free. That means adsorption has not yet started. But as time passes, what happens? Rate of condensation decreases. Whereas on the opposite side, the initial rate of evaporation is zero. Why? Because there are no molecules that are adsorbed. Slowly, as the surface gets adsorbed, okay, or as the molecules get adsorbed on the surface, what happens? The rate of evaporation becomes more and more. Okay. So that is the meaning of these two sentences, students. Fine. Now, at one stage what happens? There will be an equilibrium between the two opposite processes at which rate of condensation will be equal to rate of evaporation, students. Okay. So one is maximum initially, one is zero initially. Slowly one is decreasing, slowly one is increasing. So at one stage there exists an equilibrium between condensation and evaporation, or adsorption and desorption. That means rate of condensation will be equal to rate of evaporation. Okay, students. Now, suppose n number of molecules of a gas adsorb or strike a surface having 1 centimeter square surface area with the pressure P per second. Again, students, n number of molecules of a gas strike a surface having 1 centimeter square surface area of an adsorbent with how much pressure? Pressure P. How much time? Per second. Then the fraction of the surface area covered by adsorbed molecules will be theta. Okay, students, let us assume n number of molecules of a gas striking 1 centimeter square surface area of the adsorbent with the pressure P in 1 second. Then the fraction of surface area covered by adsorbed molecules, let us consider it as theta. Okay, the surface covered, we are considering it as theta. Now the fraction of the surface uncovered will be 1 minus theta. Why, students? Because the surface area of the adsorbent, we are considering it as 1 centimeter square. Portion of the area covered is theta. Portion of the area uncovered will be 1 minus theta. Pressure of the gas, how much? P. Now, rate of adsorption is proportional to, carefully try to understand, students. Rate of adsorption is proportional to pressure of the gas P and also the uncovered surface, that is 1 minus theta. Uncovered surface means the surface available for adsorption. Okay, the remaining surface available for adsorption. So rate of adsorption or condensation proportional to pressure of the gas P into uncovered surface 1 minus theta. Remove the proportionality. Add a constant. Suppose it is K1. K1 into P into 1 minus theta, where K1 is proportionality constant. Okay, students, rate of adsorption is equal to K1 into P into 1 minus theta. Students, rate of adsorption proportional to pressure into 1 minus theta. It is equal to K1 into P into 1 minus theta. Now, rate of evaporation or desorption will be proportional to what? Portion of the surface covered. Okay, students. So, from the portion covered only we can say, or we can find out rate of evaporation, no, students. So, rate of evaporation proportional to theta. Remove the proportionality. It is equal to K2 into theta. K2 is one more constant. At equilibrium, we know that rate of condensation is equal to rate of evaporation. So, we will make the two equations equal. K1P into 1 minus theta equals to K2 into theta. Now, remove the bracket, students. K1P into 1 is K1P minus K1P into theta is K1P theta. It is equal to K2 theta. Now, K1P is equal to, bring this to right side. K2 theta plus K1P theta. Take theta common out. What remains? K2 plus K1P. Therefore, theta equals to K1P divided by K2 plus K1P. Now, divide numerator and denominator by K2. So, K1P by K2 plus K1P by K2. Here I have written, students. Okay. Now, theta equals to K1 by K2 into P by, this becomes K2 by K2 plus K1 by K2 into P. Therefore, theta equals to K1 by K2P by K2 by K2. What happens? 1 plus K1 by K2P. So the whole thing we can write like this, students. Theta equals to AP by 1 plus AP. Why? Because K1 by K2 both are constants now, students. We can take K1 by K2 as A. So AP by 1 plus AP. But we know that extent of adsorption, that is X by M, is proportional to theta. So theta is how much? AP by 1 plus AP. Now X by M proportional to AP by 1 plus AP. Remove this proportionality, add one more constant, let us say K3. K3 into AP by 1 plus AP. Therefore X by M equals to K3 into A. This is a constant, this is a constant. So both K3 into a new constant. X by M equals to BP by 1 plus AP. Put it in a box. Here, since K3 into A equals to B. These two are constant, taking a new constant. So this is called as Langmuir adsorption isotherm equation, students. Okay. So add here Langmuir adsorption isotherm equation. I forgot to write here Langmuir adsorption isotherm equation. Okay. Now, once we derive Langmuir adsorption isotherm equation, we need to verify experimentally. Put the side heading experimental verification. Okay. For experimental verification, take Langmuir adsorption isotherm equation, students. X by M equals to BP by 1 plus AP. Now taking reciprocal on both the sides. So taking reciprocal means what? Write like this, students. 1 by X by M equals to 1 by BP by 1 plus AP. So this what happens now? 1 by X by M is equal to this 1 plus AP goes to the numerator, 1 plus AP by BP. Now 1 by X by M is equal to 1 by BP plus AP by BP, AP by BP. Okay. So now P gets cancelled. Therefore 1 by X by M is equal to 1 by BP plus A by B. Now multiply with P on both the sides. So what happens? P by X by M is equal to, okay, 1 by X by M na, students, above equation. So you are multiplying with P. So P into 1 is P. P by X by M is equal to 1 by BP into P is P by BP plus A by B into P. Okay. Therefore P by X by M equals to PP gets cancelled. What remains? 1 by P plus A by B into P. Put it in a box. Now this equation resembles straight line equation y equals to mx plus c. Now you must have understood we need to plot a graph in order to verify Langmuir adsorption isotherm equation. Now we are plotting a graph between P by X by M on y axis. Y equals to mx plus c, no, students. So P is on x axis, P by X by M on y axis. We get a straight line if Langmuir adsorption isotherm is correct. Okay, let us plot and check. Below is the graphical representation, students. X axis P, y axis P by X by M. Yes, we obtained a straight line with the slope A by B and intercept 1 by B. Okay, students. So here, hence Langmuir adsorption isotherm is verified. So this is how we derive Langmuir adsorption isotherm equation, students, and also experimental verification. Okay. Now a little 1 minute more is there, students. We need to prove Freundlich adsorption isotherm equation from Langmuir adsorption isotherm equation. That will be the application of Langmuir adsorption isotherm. So put the side heading application of Langmuir adsorption isotherm, students. So write down the equation X by M equals to BP by 1 plus AP. So here are two cases at low pressures and at high pressures. Let us see case 1 at low pressures. At low, that means pressure is low, students. In the denominator, what is there in the above equation? 1 plus AP. Okay. So pressure is low means this AP is negligible when compared to 1 as it is in the denominator. So we can neglect it. What remains after neglecting AP in the denominator? X by M equals to BP by 1. Here this pressure is low, students. So AP is being neglected. Why? Because AP is very low or less when compared to 1. So x by m equals to bp by 1. X by m equals to bp. Therefore, if you remove the constant b, x by m proportional to p. So, p I am writing it as p power 1 because p power 1 is equal to p. Next, case 2 at high pressures. Okay. Look at the equation x by m equals to bp by 1 plus ap. Pressure is high. So, 1 can be neglected when compared to ap. So, the equation becomes x by m equals to bp by ap. We neglected 1 students. Okay. So, this becomes x by m equals to b by a into pp gets cancelled now students. So, pp gets cancelled means what remains here? 1. That 1 I am showing it as p power 0. B is constant, A is constant, x by m proportional to p power 0. So, low pressures x by m proportional to p power 1, high pressures x by m proportional to p power 0. Intermediate pressures, it must follow the equation x by m proportional to p power 1 by n. Pressure to the powers 0 to 1 students, nothing but a fraction. That fraction we will write it as p power 1 by n. So, this is nothing but Freundlich adsorption isotherm. Okay students, so using LANGMUIR adsorption isotherm, we can verify Freundlich adsorption isotherm also. So, this is all about LANGMUIR adsorption isotherm equation students. It might be a bit lengthy, but it is very easy to understand. Please don't skip or don't think it is a complicated question students. Try to understand or take the screenshots and try to practice it in your ref notebook students. Okay. All the best for your exam students. Take care. Meet you in the next video with a new topic students.